All right. Hello, everyone. I'm Ambrose. I'm a West Australian and slightly jet lagged. I'll be leaving tomorrow, so it's a very brief, but it's a lovely city, isn't it? I love this place. But yeah, I've been awake for most of it. But if you haven't heard of me or what I do, I'm very much in the Clojure development thing. But my work is summarized as type Clojure, and it's an optional type system for Clojure. And this talk, I kind of, not really intentionally, but I figured out, stepping back from type Clojure a bit, and I was comparing it to the way that linters work, and I guess I saw something interesting, the correspondence between the two things. But this talk is really just going to be going through some of the features that type Clojure has, maybe letting you know the types of things we can do with optional type systems, and maybe getting you thinking about how they can be used in maybe your favorite language or where you might want one. So yeah, I started work with type Clojure in late 2011, and my undergraduate honors dissertation was on that, and that's the name of it at the top there. And last year I did a crowdfunding campaign to start full-time development on type Clojure, and I've been lucky enough to have been working on type Clojure since November full-time. So that's awesome stuff, and that's my Twitter handle if you want to follow me. So really the big idea of type Clojure is this idea of a pluggable optional type system. And the things that are implied when we're talking about a pluggable type system is that they don't affect program semantics. So you should be thinking linters right now. Like usually you have your program over here, your compilers and stuff. Your linters is something else you can run it at the command line, maybe at the REPL or the console or something like that. But it's really quite separate from the process of compiling your programs and maybe optimizing it and things like that. So one very cool thing that comes out of not affecting program semantics is that we can keep all the same tooling. So type Clojure is a library. It's just a jar you bring in. You just require it as you would normally in a Clojure project. And I use a Vim plugin for Clojure. I use the same plugin. I use the same .clj file extension. So basically, the tooling doesn't need to know about what I'm using on top of type Clojure. On top of Clojure. And this also implies that we can layer on arbitrary amounts of these type systems. But to be honest, I've been so much in the type Clojure world just building one. This is like a different idea than something I've been used to. But it's starting to occur to me that there are interesting things we can build on top of type Clojure. And just recently I Googled Java 8 and optional type systems, and I found out that Java 8 will support pluggable optional type systems, which kind of blows my mind, which is pretty amazing. And it basically looks like an annotation. Say if you wanted a verification pass that would look that would try and prevent null pointer exceptions, you would add a particular annotation to a particular type and then run the verification tool, and it would be a pluggable type system, and it would use that extra information to tell you more stuff about your Java programs. So I think that's very cool that pluggable type systems are coming into the mainstream. So if you haven't heard about Clojure, it's a Lisp dialect. It's a dynamically typed language, and it's designed to be hosted on VMs like the JVM and JavaScript and CLR. And I guess I just listed my favorite feature of Clojure, which is immutability, but I'm not really here to specifically to tell you about Clojure, just some of the dynamic idioms that we use in Clojure and how we try and check them with optional typing. So yeah, if you've never seen Lisp, this may help, I don't know. But you may be used to that left paren being one form to the right. Just in your head, do the transformation. But basically a function call in Clojure everything's in the parentheses, and the function is at the first entry in the list, and then we have our arguments. And I don't assume anyone's got any Clojure experience, so I'll be meticulous in stepping through any code that's particularly important. So some of the goals of type Clojure, I've already gone through a few of them. One is to have a type checker as a library, and the next one is to understand common Clojure style, and this kind of has some benefits and some not so good things. But some of the benefits are that we can take our normal Clojure code and start type checking it without rewriting our programs, and that's kind of a really important thing with type Clojure. I want programmers to be able to import type Clojure and start adding annotations. So I only want additive changes. I only want, there's particular places you need to add annotations in type Clojure. I don't want people starting to write loops inside out just because type Clojure isn't smart enough. So that's a very important thing to understand how Clojure programmers use Clojure, the most common ways, and to model them in terms of a type system and the way that it reasons about things. And kind of I guess a footnote is that I've designed type Clojure to be sound, so I haven't put any obvious backdoors like in TypeScript or Dart and things like that. There are certain, I guess, certain intentional unsoundnesses that are justified by social reasons, I guess, but I ignore that. I had to write a dissertation, so if it's unsound, it's pointless. So, but it's cool stuff because we can actually start, leaning on the type system. Perhaps not as much as a language like Haskell, but we can enjoy certain invariants. And basically, once your type system becomes unsound, you've just lost any hope of guaranteeing anything. So type Clojure gives you some guarantees, which is nice to have. And we'll go through some of them. We've gone through these. The type system, don't expect type Clojure to do some amazing automatic type checking. It's very much, if you've used Scala or something like that, it's kind of like having the equivalent of Scala annotations inside your Clojure programs. So it's very much local inference. We're not trying to do what Haskell or ML does and do global type inference. And this means that there are specific places where annotations are required. For example, top-level vars, function, local function arguments, and there's a bunch of other places where that can be inferred. So it ends up being somewhere between Java and Haskell. No. Well, it's kind of like Scala. It's a bit more verbose than Scala, I guess. So one cool thing that we have with pluggable type systems is that we can get out of this kind of cyclic pattern, development pattern that we have here, that we have with traditional type systems. So if you've used Java or Haskell or any statically typed language, this kind of development cycle should be familiar to you. Because once you press compile, you're going to get a type error at some point, and you're kind of stuck at that point. And this is kind of intentional. This is the way that statically typed languages work. If you don't pass the type checker, your program doesn't have any semantics. So that's it. You have to pass the type checker. So in a way, it's kind of a bottleneck. And if the type system's good enough, then it's a fantastic bottleneck to have, because you just keep on type checking things, and eventually things will it'll direct you as to where to go. But if your type system isn't all that good, then this process can be somewhat annoying. But once we move to pluggable and optional type systems, we kind of get this separation of the two phases, I guess. And if you replace the bottom type check with lint or something like that, it should be fairly obvious what the process is to kick off, I guess, type checking. It's some command that we run at any point, and we can package it up with any other operation. So you can imagine we can reconstruct the whole cyclic development of that pipeline of type checking and running by just combining these two operations. So this is kind of when I use type closure, this is pretty representative of the way I use it. I like to mix verification techniques. I use unit testing, generative testing, and just REPL development, and these kind of rapid iteration things that dynamically typed languages are kind of famous for. So yeah, if your code can't run if it doesn't type check, then you obviously don't have access to all of those things. So it's a nice thing. If your type system is pluggable, then you can have access to all those other verification techniques at any point. So this is, from here on, we're just going to have a look at the types of things that Clojure has, and maybe as we go through, kind of compare it with the way that your favorite language might do these particular things, and yeah, to just consider how you might use a type system like this, and maybe if your language already has an optional type system, maybe it'll motivate you to go check it out. So we're just going to start really simple. Clojure is built on the JVM, and on the JVM we've got classes and primitives and null, I guess, objects, I mean. But unsurprisingly, everything in Clojure is an instance of some class. So in Clojure we use in type Clojure we use the same kind of concept. So the top form there is a symbol. So it's an instance of a Clojurelang symbol, and somewhere there's a Clojurelang symbol.java in the Clojure implementation. And you might be more familiar with javalang long. That's the default. That's the class of an integer that when you type it out in a Clojure program, it's not a javalang integer, it's a javalang long. And there's a couple of other types. There's a top type, which is any type, and I just put some expression. You can substitute any expression, that's of any type. And if you throw an exception, that's a type of nothing. So here's a function type. It's a local function. There's some pretty ugly syntax there, but basically we're annotating the argument to be of type number, and you can see the type in red. Everything to the left of the arrow is a parameter. Everything to the right is a return type, and you can see we have to annotate the parameter types just because of the way that local type inference works, and yeah, we can infer the result type. So we have these nice ways of talking about collections. In Clojure, we prefer immutable collections, and we've got a nice suite of performant, immutable, persistent data structures. So on that first line, we've got a vector with some different types in it, and you can see the type says it's a vec, or a vector of a union. So that type there is a union, and we can basically cram as many types as we want in there. It's an untagged, ad hoc, messy union. It's as messy as you might expect. It's as messy as Clojure needs it to be, because in Clojure we can combine any amount of types to flow in and out of expressions. So it's sufficient to model this. And yeah, with maps, the second one, the second form, yeah, it's a map from number to number, just showing you those things exist. So yeah, types can get big. We've got type aliases. It's really nothing special. It's an abbreviation. Everything gets expanded out by the time we do type checking. So I'll be using a few type aliases. So we looked at the unions. It's all well and good to cram these types into a union, but the problem is, what do we do once we want to actually apply something of that type to an operation, right? So you can imagine at the top of our program, we might have a massive type that says this could be a number, symbol, keyword. It's like, okay, great. At some point, we're going to want to maybe increment that. So what type closure basically does is use a particular inference style called occurrence typing, and this was invented for typed racket. And if you haven't, type clojure is very much based on type racket. I've stole as much as I can from it, and I'm still stealing it from it today. And the basic idea is, as we get further into our program, kind of diagonally, if you think of this way, if you think of a conditional as kind of a diagonal branch, as we start going further into our programs, we learn more information. And just the way Clojure programmers use conditionals, we can learn a lot about program flow. And you can see on the first line, we've got a local binding, and there's some conditional. And basically, just to go back a few slides, I forgot to talk about this. But if we have a conditional, and to read this as just an if statement with a then, else, and test, then, and else, you can see that the result of this expression has types being fed from the then and the else branch, and you can imagine any combination of types coming from this. So basically, I've reused the same thing on the right-hand side of this first line. So the local binding A is going to be a union of symbol and number. And just in regular Clojure, if we wanted to use this, we'd have to figure out at runtime what exactly this is. So we need a dispatch of some kind. So in the if statement, we're asking if A is a symbol, and there's this operation in Clojure where we get the name of a symbol. It returns a string from, it's a function from symbol to string. And we can see just by looking at this that this is going to be fine for the then branch because we've got a symbol in there. If we look at the else branch, if we kind of figure out all the cases, then clearly the else branch is going to be well typed as well, because if it's not a symbol, then it's a number, and we can increment that number, which is the inc operation there. And this is this idea of narrowing and eliminating unions with occurrence typing. And local bindings in Clojure are immutable, which is a pretty crucial property with this sort of inference. This type of inference happens automatically, and this is kind of the form that type Clojure finds things once it's expanded out all your programs. Everything expands out into if statements. And if we wanted to learn more about our programs while going kind of while sequencing operations, then we can use assertions, or just literally throwing exceptions. Assert here is just a macro that throws an exception if the condition fails. But type Clojure can figure out that, okay, on the second line we're asserting that A is a number. If we've gone past this, then clearly A is going to be a number. Otherwise, we've blown up already. And this is a type Clojure kind of takes has a few opinions about which exceptions are better. We're fine with assertion errors. That's just part of programming in Clojure. Things like null pointer exceptions we've eliminated in typed code. But yeah, asserts are fine, and you can imagine by the time we're in the third line, type Clojure has figured out that A is going to be a number, and therefore this is a well-typed operation. And if we didn't have that assert in there, it would complain that union of symbol and number is not a number, so we can't increment it. So one of the coolest things about Clojure is we're emphasizing data, but probably one of the most horrific things from a type system perspective is that we explicitly do not want to declare our data in advance, or at least that's the norm. It's great when we're developing things, we can just change a particular field in one spot and maybe gather it in another spot in our program, but there's no kind of schema or explicit structure that we can use to check. So type closure is very much optimized to understand the common ways of manipulating data in Clojure in such a way that you can prove some pretty interesting properties with them. So this is definitely my favorite area with type closure, is this idea of a heterogeneous map. And all it is just it's a map that knows some information about keyword entries. So it knows which keyword entries are present, which ones are optional, which ones are, and whether the map is partial, whether there is extra keys that we might not know about. And there is some support for some common operations like adding and removing keys, merging maps, and things like that. So starting off dead simple, we've got a map, literal, and in Clojure, to make a keyword, we just put a colon before the symbol. And you can see that we get a few bits of information out from here. The types in green are telling us that we've got 3 mandatory entries. And at the bottom, we have some completeness information. And you can see that just because it's a map literal, that there are no extra keys that we need to worry about. So type closure remembers this, and it comes in pretty useful in some of the operations that we use. So just associating and dissociating elements from a map, just adding and removing. And when I say it says modifying maps, but remember these are immutable data structures, so we're really returning new maps for fairly cheaply with structural sharing. But the first expression, we're associating a B entry onto a map that's already, it's got a mandatory A key and it's complete. So there's this invariant, if you associate, if you add keys to a map that's already complete, then it's clearly still complete, so we preserve that information in the return type. And we've got a new mandatory key, this B key. And we preserve all the mandatory keys from the first argument of assoc. And with dissoc, it's kind of the same. We remember the completeness property and just remove whatever key we're removing. And this is basically the same as saying mandatory with an empty map. So looking up maps, we can, the simplest case up the top, we're just looking up a keyword A in the map with one entry A, and this is always going to return a number, so yep, type closure can figure that out. So it becomes more interesting when we have unions of maps that we're feeding into the lookup functions. So if we see this conditional, the if some condition, then we get out a map with an A key, otherwise we get out a map with a B key. So one thing in Clojure is it's very much emphasized that things return nil instead of throwing exceptions. So type closure has to follow this lead because of the things we were talking about before with being able to port untyped code to typed code without having to rearrange our programs. So we need to understand this invariant. So you can see if we go down the else branch in this if, there is a possibility we will return nil. So yeah, the return type there is a union of nil and number, and I guess the number comes from the first branch of the if, and the nil comes from the second. So this is pretty cool. We can track information about merging maps, and where do we start? So the first, when we merge maps together, the maps to the right are always taking precedence. So if there's duplicate keys, then the map to the right will win. It will use that entry. And so the map we have on the left, as in the first argument, you can see it's going to be a union of 2 maps. So the first branch has an A key and a C key, and in the else branch in the blue we have a B key. So you can see that depending on which branch we have, it's going to be an option. We're going to either have an A key or a B key. So you can see in the type, there's a red and a blue entry in the optional constructor in the HMAP constructor. Sorry, an optional option in the HMAP constructor. But what the optional option says, the optional keyword argument, let's call it that. It basically says that, let's look at the red optional key. If A is present, it must be a number. Otherwise, it must be absent from the map. And yeah, so a mandatory key says it must be present and it must be a number. So there's a few things going on here. You can see in the then branch, we've got on the second line, kind of in a grayed out font, that we've got a C key up there, but it's a symbol there on the second line, but you can see it's not actually represented in the type, and that's because by the time we merge it with the map in the second argument, it's always overwritten. So I guess I'm trying to get across that there are a lot of things going on just merging things, when you're just merging maps. And this is kind of simple because everything is a complete map. Once you start having things that are partial and you don't know certain information, you might accidentally be overriding keys. So I guess there's a lot of things going on in the programmer's head that we need to keep track of. And type Clojure is giving Clojure programmers some facilities for reasoning about these sorts of computations. And yeah. So we saw occurrence typing before, the way we eliminated unions as we went further down into our programs, down branches. It turns out this also works inside nested maps. So you can see that the expression in red is the same expression we had before, but now it's nested inside two maps. The first map has an A key, down the B key. And so to get to the expression in red, we have to go down the path A and B. And that's basically what these expressions in blue is doing. It's going down, it's saying apply the A key and then the B key to A, and then give me that result. And the test is saying, is the value down the A and the B key a number? And we then use this information in the then branch on the fourth line. And at that point, type Clojure actually updates the type for the local binding for that red expression to be a number because of what we've learned from the test. And just like before, in the else branch, we've updated it to be not a number, so therefore it's a symbol. Therefore, the name is a well-typed operation there. So it's very common in Clojure to represent our data in terms of maps like this. And instead of having something that's declared up front with very rigorous keys, you often have a specific key that we dispatch on. So if we were writing a compiler, say, we might have a map representation of our expressions. So from the top line, we've got a def alias. So we're defining an alias called expression, or expr. And then we're defining a recursive type. So we're just calling it expression here. And this is kind of, it looks a bit redundant. I guess it is, but this is just the way that type Clojure can use recursive types with subtyping. But yeah, just kind of ignore that second line. It's just needed. But you can see that the expr is scoped inside the rec, the recursive type. And there are a couple of keys in common, and you can see that if we wanted to discriminate between these different maps at runtime, we'd have to test these keys. So the op key in blue would be the key that we're going to look up, and if the two values in red are up the top, if it's an if statement, then clearly it's going to be this first expression. If it's a do statement, it's going to be the second case. And very often in Clojure, the way we deal with these, or the way we process maps like this is with a multi-method. And basically the def multi in the middle of the screen, it sets up a multi-method that dispatches on the op key. And it basically looks up the op key and then finds any def methods that are that correspond to the operation, to the value that we get out from the op key. You can see that the first def method, so def method pass if. You can imagine that at that point, the if, we know that the op key is if. So type Clojure is smart enough to figure out that all the other different members of that union can be eliminated. So once we type check this def method, we can treat it as if it's just the if statement, the if expression, and the same thing with the do. So type Clojure has some interesting rules with respect to Java interop. So Clojure has some nice interop facilities with Java. We can do all the normal things, call methods, make objects via constructors, and look up fields, all these nice things. But turns out that Java's type system has a few holes in it, at least from the perspective of trying to communicate with it from type Clojure. And the biggest hole is the null pointer. And if you've ever used Java, you'd know that once you see an annotation like Java lang integer, in your head you're thinking, okay, from the invariance of Java's type system, I know that this really means a union of nil and an instance of Java lang integer. And I didn't specifically say it before, but you saw that we're using nil as a specific type. And I've managed to pry apart the two concepts. So when you see Java lang integer in type Clojure, that is a non-nullable type. And then nil is just another value. It's nothing special. And I guess to be explicit, nil is the same thing as null. Once null goes into Clojure, it's nil. So yeah, there are some interesting rules to try and protect Clojure programmers from anything crazy that might be seeping into their programs from Java. So I try and be as, type Clojure is very pessimistic by default. You cannot pass nil to a method, and you always expect the worst. You always expect that somehow nil is going to come out of a method. So yeah, this is overridable by the programmer, and it is a hole in the type system in the sense that I kind of punt here. I give up and say, okay, you better get this right, otherwise bad things are going to happen. But there are some invariants that type Clojure can take advantage of. For example, in Java, if you call a constructor, the return type is non-nillable. That's just an invariant of Java. So in type Clojure, we don't expect a constructor to ever return nil, so we don't need to tell that to type Clojure. Things like fields, we assume are nillable. I guess the other craziness in the Java type system is an array. And basically, it comes down to you can't trust the type of an array. And I did have a solution to this, but I guess I won't really talk about it because I wasn't very satisfied with it. I need to revisit it. But I did include it in my dissertation. It was like a little chapter, but I probably should have tested it a bit more before I put it in there. So Clojure's a Lisp. It's very functional, very much an emphasis on higher order functions, first class functions. So naturally, we have really nice support for typing functions. We have what's called an ordered function intersection. Again, completely yanked from type racket. And I'm very glad to hear that TypeScript yanked it as well, because they're really nice. They're a really nice idea, and I'm glad it's kind of making it into the mainstream. But yeah, it's it's an ordered list of arities that represents a function, and it basically encapsulates all the different ways you can call a function. So let's start really simple. If we just have one arity, there's only one way to call the function. And this, I don't think we've seen this before, but this is the way we annotate things in top-level vars in type Clojure. We use the an form and just name the var, and then we have our type. And you can see we're annotating this as a number to a number, so this is an ordered function intersection, but it happens to have only one case. But once we have multiple cases, in the middle here you see another an expression. And you can see there's an fn constructor around the vectors now. That's the other syntax was just sugar for this fn syntax. And the way to read this is basically kind of like a conditional or a pattern match in that it's a top-down thing. So type Clojure will try each case of your function type and figure out if it's well typed. So for example, if you're trying to apply food to a symbol, it'll try this first arity on the this number to number. Okay, a symbol isn't a number. Okay, let's try the next one. Yep, a symbol is a symbol. Okay, that's great. And then we return a string. So if we fall off the end, that's a type error. So yeah, it's very common to have the last arity of your ordered intersection as the most general. And if we follow the aliases up the top, it's a number sim is just a union of number and symbol, and number stir is a union of number and string. And you can see that it kind of encapsulates all the different ways that we could call this function. And the first and second arities just make it nice for the programmer not to have to cast values all the time. If we know that a number is going to give back a number, we can add this as a more specific case on top of the more general one. So we can encode keyword arguments as well. The syntax for this, on the first line, you just have the and optional keys for optional keyword arguments. Very much works like the HMAP we saw before. So mandatory means you must provide it. Optional means you must provide, if you do provide it, it must be the type that you give it, otherwise you must omit it. So you can use all the same syntax we use in Clojure. On the second line, we have some destructuring, which is the way we pull apart our maps. And again, once type Clojure has your Clojure program, it's completely expanded out, so type Clojure doesn't have to worry about destructuring itself. It turns out it's just a normal keyword lookup that we saw before. So it's really reusing the same infrastructure that we use to check a HMAP. And you can see the call down the bottom, you can see that would type check because keyword is a number, and yeah, it's fairly straightforward. So there's a couple of ways to introduce polymorphism. I'm going to concentrate on polymorphic functions and very briefly show some bounded polymorphism that might look more familiar if you've used Scala or something like that. So here's identity, most boring polymorphic function I could find. But you can see we've got an OR constructor that scopes some variable x. And the way to read this is say, for all types x, this function takes an x and returns an x. So it returns its argument. And yeah, this type checks as you'd expect. To go to the complete other end of the spectrum in complexity, we've got maps and assoc at the type level and other craziness. But basically, what I was trying to do here was encapsulate the idea of adding a key to a map and abstracting over that idea. Because once we associate a key to a map, we saw that there are interesting invariants that get propagated through. If we associate a map that was complete, then it's complete when we associate things. If it's partial, then it's partial when we associate a thing. And we need to remember if we're overriding keys or anything like that. So This type up the top is basically saying that this, I might as well come around and start waving my hands. This X up here is a map that's being scoped by this all binding, and it's got an upper bound of a map to any. So you can pass any map to this, and you can see we actually are passing maps to this. And if we substitute in the type for this, which is a H map of, it's a complete H map with a mandatory key of B. So let's substitute that in for the X. What the all does, it basically tells us all the different ways we can call a function. So we just substitute in a type, and it tells us a way to call it. So if we substitute a HMAP type with one mandatory key and add it, substitute that X for it, and then this X here as well gets substituted, you can imagine that this assoc operation is pretty much the same assoc as we have here. It's this on the value level, but on the type level here. So we're associating onto the HMAP type. So basically what happens here is this B gets substituted in here, and then the HMAP is updated with this extra entry of an A to a number. And actually, invoking these things, you can see, I guess this first one is the more interesting one. If we add an A key to this HMAP here, then clearly it's always going to be a number, just because of the way, where the number, because the A key always has a number entry there. And this second line shows off that, hey, we haven't forgotten about this B. We always know that looking up this B, even if we add an A and we increment it, that's not going to be a type error as well. So this is pretty cool stuff. Dotted polymorphism. I'm not actually going to explain how it works, but the basic idea is that in Lisps and in kind of dynamic languages, it's very common to have a pattern of repeating arguments that go on till infinity. But there's usually an interesting link between the arguments. And if you've ever used map, you've probably used this arity here, where you pass a collection and then feed the collection into the function, right? But in Clojure, it gets a bit more interesting, or in any Lisp. You can add several functions, you can add any number of collections, and each member of the collection is applied to the function kind of simultaneously. So here, the 1 and 4 is applied, then 2 and 5. You can imagine this will go on forever. And you could also imagine trying to annotate this, that it would go on forever, your annotations, and you have to give up at some point. But basically, dotted polymorphism gives us a way to define a template for this invariant. The real invariant is that the number of collections that you give, so 1 here, has to equal the number of parameters that this is allowed to take. So, okay, plus can take 1. Yeah, so we've got 2 here, so this can take 2, et cetera, et cetera. Plus can take any number of arguments in Clojure. So the second invariant is that whatever type we feed into the function has to, be a valid way to invoke that function. This is a very simple example. So everything is numbers, so clearly everything's fine. But I guess there was a function that took a number, then a string, and then a foo bar or whatever. We'd have to make sure that we've got numbers, strings, and foo bars. And hopefully that makes a bit of sense. Yeah, it basically allows us to express these infinite invariants related to variable arguments. So it's very nice having macros. Who would have thought? But In Lisp, we have macros, and it turns out types and macros are really nice because you can roll your own syntax. You don't need to wait for me to roll out of bed and start implementing some macro for you or some primitive where you want the type directly in this particular spot. Just get out def macro and start coding it. And it's kind of there aren't very many pretty things in type closure right now. Kind of one reason is I've been doing other things. I've been working other parts of the type system. Another reason is you can just write your own, and please do, because that's the whole point with macros. And just the simplest example, say if we look at this expression in blue, if we just wanted to be able to insert, instead of doing something like this, where we annotate the var and then have to have a def, we might want this, the type to be directly after the def. And you can, if you're not familiar with macros, you can kind of see how the shape of this, this code here corresponds to here. We're rewriting these two arguments here. You can see there's the underscore and the t, and we're kind of slotting them in where they need to go. And it's kind of a lesson on how cool macros are, but it turns out that it's really nice to be able to roll our own typed operations. And once we start type checking libraries, like I've tried type checking just for fun. There's a graphics manipulation library called Quill, and then there's Overtone, which does music generation. And it turns out that there's some pretty crazy macros in there, but we can make it quite pretty by making more macros, I guess. But if we can always make it pretty with one more macro. But you can see how easy that was. Hopefully that convinces you that it's a good idea and it's nice and pretty. So yeah, so the big idea that we have here is that pluggable type systems can really live on top of your language without having to be particularly invasive, in the sense that we can keep our compiler, we can keep our tools, keep our editor, keep our file extension, which is great. And we don't need to worry about those things. You know, yeah, we don't need to implement our own compiler. This is great if you're just one person like me. But if you're Microsoft and you can write TypeScript, and that's very nice. But if you're just one person, this is great stuff. So yeah, it's very much like a linter in the sense you can have, you're like, oh, today I might want to prove a particular thing about this bit of code, or I guess there's any range of things you can do with a type system that are kind of comparable to linting, depending on how sound your type system is. But I guess the thing that I hope you walk away from in this talk is the kinds of things that are possible right now, type checking these dynamic idioms, and perhaps trying to start thinking about where you can use it, or start wishing where you could use it in your own language. And it really exposes the differences between languages by trying to write a type system for it. The HMAP constructor we saw before, that isn't in type racket. And it's not because type racket, the guys were too lazy to implement it or they didn't get around to it. It's because racket doesn't use maps the same way as Clojure does. So you end up learning a lot about your own language in very kind of precise terms. Yeah, we saw that there are many invariants flying around. You just don't need to worry about that in racket because of the way people program. So yeah, it's very much a learning experience about your programming language as well. So I guess I'll take some questions and comments. I've got a microphone coming around.
Can you explain the distinction between occurrence typing and dependent types?
Sorry?
Can you explain the distinction between dependent types? I'm sorry. Can you explain the distinction between dependent types and occurrence typing? I know a little bit about dependent types, but I've never seen the occurrence typing.
I don't know much about dependent types, but I know a lot about occurrence typing. Basically, the idea is we have, it's probably pretty close to a dependent typing, but we have this idea where we have types, we have our bindings, and then we have propositions, which is a way to relate our bindings to our types. So if we just had a simple if statement that said, if A is a symbol, then go down the then branch, otherwise go down the else branch, we generate a proposition that says, that gets added to the environment down the then branch, and the proposition says A is a number, and then we also have the same, the reverse proposition in the else branch to say A, oh, did I say number? I meant symbol. But then we have the reverse that says A is not a symbol. And you can imagine if we mash together that proposition with the union that A is a union of symbol and number, then we get out a different, a more accurate type. And the way the H-map thing works, where we saw where we're narrowing the type of a value that's nested in a map, it's just extra information on your proposition. So if we have a symbol predicate on a lookup down a map, it's down the then branch we have A is a symbol down the A-B path, and then you have the opposite, and then type closure kind of mashes them all together. And occurrence typing is very optimized to having immutable data structures and immutable bindings. So it's not really applicable to something like JavaScript, to type checking JavaScript. There's a project called Dependent JavaScript which uses, I forgot what they're called, constraint and resolution, big things, what are they called? Things that Microsoft build. I forgot. Yeah, constraint solvers. Yeah, sorry, I'm tired. But yeah, you have to, once you have mutability around, you have to keep track of a lot of things. But with occurrence typing, it's kind of a very cheap, nice way of of reasoning about immutable things. Yeah. So any other questions?
So just so that it's clear in my head, the occurrence typing helps determine the type when you're within the form, right? Because the type of the outermost form is still union of string number or whatever, right?
Yeah, if you imagine type checking as just walking down the trees, right? Okay, we're down this branch. What have we learned? Okay, update it. Let's keep going. And then, it's just backtracking. Then we lose information as we go out and then come back in. Yeah. Any other questions? Yep. This one here.
Is there anything that helps us to check the annotations themselves? Because looking at one of the examples, it seems like there are more annotations in the code. I was just curious if
to generate them?
To check annotations, whether they,
Well, if you have the actual code there,
yeah, like the slide, right?
Something like that. Type closure, once it gets to the defen, it uses the type you give it to kind of drive type checking, and it does actually verify that the X's all line up there. The interesting part is, how do we verify?
That's what you meant to have.
Sorry, yeah. Oh, no. That is, I'm not, there's no magic going on there. Like, you have to give it the right types. I'm not telling you if you're a bad programmer. I'm telling you if you're going to blow up at runtime, right? That's kind of the main invariant with type closure and a lot of type systems, that you're not going to have specific type errors. I'm not telling you how good your code is. That there is an interesting issue where at some point you can imagine there's untyped closure and then there's typed closure. So there's two completely different lands, and there's this interface in the middle, and you've got to be quite careful what you feed in and out. And type bracket actually is very very strict with the data flow here, and it actually generates contracts to preserve soundness at runtime. This is something that type Clojure doesn't do, and I'm going to add it soon. But that's where it really gets interesting, how to deal with that interaction.
Thank you.
Yeah. Yep.
So if I make a call to an ordinary untyped Clojure function, def and foo in some other library, is the return type always inferred to be object?
The way it works currently, it says, hey, it's a type error, you haven't annotated anything. So that interface in the middle has to be annotated. The way it works currently, it's this no check annotation that says, okay, let's just, I'll just trust you, programmer, that it really is this type, and then type Clojure assumes that that the type you've given the untyped binding is actually correct. But that contract generation I was talking about just before allows us to enforce that at runtime and make sure that, and the other big idea is that by generating these contracts, we can also pinpoint the blame, exactly who's to blame, right? And it's usually the untyped module giving bad things to the types, or it always is. And well, it's called the blame theorem. It's the coolest name ever. But yeah. Any other? Yeah.
I was just also wondering if there's any kind of tractability proof on the type methods that you're using.
What do you mean by that?
Like, it just seems very complicated to do all the type checking.
Yeah.
Are there programs that it would just run for a crazy amount of time?
Yeah, but mainly because I'm a bad programmer and lazy. There's some nice properties about having explicit annotations. We don't have to do some global inference that might iterate on and try and find some stable fixed point. It's very much, okay, let's give an expected type, and we just have to check a very localized area. And actually, the place where it does actually run forever at the moment, and it doesn't do it in type bracket. It's my fault. But you can imagine if we have a conditional that has a very long conjunction. So the conditional test might say if A is number, B is symbol, C, D, E, F, G. Okay, that's great for the then branch. But then we have to invert all that for the else branch. And I think I'm being a bit too smart, and the propositions just explode by that point. That's really the place where I need to look at to optimize. But yeah, the type checking is complicated. Anything using subtyping is pretty complicated. But yeah, things like error messages are localized. The performance is very much localized. You can comment out code and figure out exactly where the type checker is hanging, for example. So we're not trying to figure out some global stuff. It's very much local. Yeah. Is there another question? I think that's it. Thank you.